yesterday at the end of class, I'm like, do y'all want me to rush through this example before the bell so y'all can be at the same point as third? And y'all were like, yeah, it's like the others, it's good. Well, since we're doing what we're doing, we're going to do chapter 7 in its entirety. So we're going to pick up where we left off yesterday at the end of the hot sauce example. So it's kind of 2/3 of the way through page 23. Make sure you have your notes out. Make sure you have your Z table out. And dual credit, were y'all able to find the review that I posted in Blackboard? Or have y'all looked for the review that I posted on Sunday in Blackboard?
No, I haven't had any push through.
I found it, I think.
You found it?
The one for that's gonna be today?
Yes.
Yes. I forgot where I found it.
Okay, yeah, so,
Is it this one?
yes.
Okay.
So, on Blackboard, if you haven't found it, you'll click on Test 2 Materials, and then it'll be all the way at the bottom of the Test 2 Materials. So, maybe that's something you want to look at. Print out or pull it up on your phone with your homework sitting beside you and start going through. Circling things, highlighting things. I'll be here after school today if you want to come by today and ask questions. Before I forget, Yancy, are you taking the test today? Was that the plan, or the makeup test?
I was beginning today, but I don't know, because like I was kind of helping with economics and today's orientation.
Okay. Yeah, we gotta make sure we get that done before next Friday. Then it stays. That's the end of the 9 weeks.
Friday.
This Friday, tomorrow?
Yeah.
Yeah, I guess you can stay. I wasn't planning on staying on Fridays, but you can stay. Okay, so we have this hot sauce example that they claim there's 20 ounces in their jar, but really the mean of it, as a recap, the mean is actually 20.2 ounces. Standard deviation was 0.125. Okay, they ask us 99% of the jars of this brand of pecani sauce will contain more than what amount of sauce? Well, if 99% contain more than a certain amount, what percent contains less than that amount? 1%. And why do we have to do less than? That's right. Yeah. So our table, well, main reason is our table only gives us less than. So our table only will give us the less than amount, not the greater than. Yeah. So what we want is the probability that Z is less than Z star to be 0.01. I guess really I need 2 zeros after to make sure I line it up with the table. So I have to find my Z star in the table. So this is where we want to look for 0.01 in the body of the table. And then trace outwards to get our z. Yeah, you're right. It's negative 2.33, yep. So let me just recap. It won't be the same number, but I just want to recap what we did in case someone was kind of confused. Oh, here's our table. Conveniently, we were looking up the same percent. Oh, that's because this is the solution to that problem. Oh, okay. Like this. There we go. Okay, so we're going to look in the body of our table. These blue cells are where 0.01 is kind of in the middle here. Somewhere in there. So then we have to pick which one's it closer to. Closer to the 0.0099, which means I want to use this column and this row. Negative 2.33 is my z. Let me go back. Z star is negative 2.33. But remember, it's not asking for z star, it's asking for the amount of sauce. I'm asking for a z. That's where I have to set up my standardization procedure. X minus the mean of 20.2 divided by the standard deviation is equal to negative 2.33. Then what do I need to do to get rid of that 0.125 at the bottom? Multiply both sides by 0.125, and that gets me what? Something, going to be negative something. I'll just leave it at negative 0.29. Then I got to add 20.2 over. And what does that get me for the number of ounces? 19.1? 19.91, there you go. And of course we're dealing with ounces here. I shouldn't box in. I need to break that habit. So now on the AP test, they don't want you boxing your answer. Yes.
What's wrong with boxing?
What's wrong with boxing it? Because they look at the whole, everything you write down, they look at as your solution. So if you box it, you're saying, okay, this is all I want you to look at. What's in the box. That's what you're telling them.
So like if any box is wrong, we'll get the entire thing wrong instead of part of it.
That's right. Let's say here you put 20.91 and you boxed it in. They're just going to look at that and say 20.91. Nope, wrong. No credit. They're not even going to look at all the work and see, oh, well, he just made a math error. So it's partially right. That's wrong. So that's why you don't want to box it in. Okay, questions on this one? Okay. These are the solutions that we already looked at. Cereal example. The weight of the cereal in a box is normally distributed with a mean of 12.15 ounces. Mean of 12.15 and a standard deviation of 0.2. What percentage of the boxes have contents that weigh under 12 ounces? We want the probability that X is less than 12. Now, can I just go straight to my Z table at this point? X is less than 12? No, what do I have to do? Let's standardize it. That's equal to the probability that Z is less than 12 minus 12.15 over sigma. Which is the probability that Z is less than what? Negative 0.75. If we use our table, what would we get?
.22.
0.2266. Good. Now what I have got for I'll do as far as answers go, I just draw a line underneath it to show I'm done. And if you look at like an example on the textbook, notice they won't box the answers in. They usually do something like a little box and color it in. That kind of shows, okay, example's done, or problem's done. That's it. Okay, questions on this one? Onwards to the next. Turn printer example. So the time it takes to first encounter the failure of a unit of a brand of inkjet printer is approximately normally distributed with a mean of 1500 and a standard deviation of 225 hours. So mean is 1500, standard deviation is 225. What proportion of these printers will fail before 1200 hours? I want the probability that X is less than 1200. Which means I need to standardize. Probability that Z less than 1200 minus 1500 over 225. What do we get for Z value? Negative 1 point. Is it 3.3 or 3.4? 3.3. Then we can look in our Z table and find the probability is what? Point 0918. Questions on this one? Okay, part B. What proportion of these printers will not fail within the first 2,000 hours? So in other words, we want the probability that X is greater than 2,000. Okay, so let's standardize first. The probability that Z is greater than what? Oh, wait, that should be 1,300. 2.22, yep. Yep. Is mine Z? Well, that's less than 2.22. Remember, we want greater than, so I'm going to have to subtract 1 from that, or subtract that from 1. And that gives us our probability. Okay.
Do the same stuff we did yesterday?
Yes.
Alright. Mr. Schultz, what did you have for lunch today?
Honestly, it's the same thing I've had for lunch every day. So I took some spaghetti squash and roasted it on Sunday, and then made a homemade Alfredo sauce with and mixed in a little bit of marinara sauce to make what Warren would call a pink sauce. It's like half marinara, half Alfredo with blackened chicken breast in it.
Oh, good. Spaghetti squash, no joke.
It is good. I'd rather it than noodles.
It tastes just like noodles.
Okay, I don't really like.
You don't like vegetables, it's not really.
Yeah. Okay. So this is just the answers here. Okay. Evidently, I didn't make a slide for part C, but we're still doing it anyways for the practice. You have it in your notes, so you can read along with me. What should be the guaranteed time for these printers if the manufacturer wants only 5% to fail within the guarantee period? So we want only 5% to fail. 95% are good. What we want then is the probability that Z is less than Z star to equal 0.95. We want 95% to be good. Like I said, this is for B, the picture and the question. I don't have a slide for C. We're just taking over B for a second. Okay, now, how do I find my Z star? What number do I look for in the middle of the table? 0.95. We'll look for 0.95 in the middle of my table.
Yeah.
They're the same distance, so let's split the difference. 1.645. The Z star will be 1.645. Okay, but it doesn't ask for what Z star is, it asks for hours. We're going to have to set up our standardization procedure. I don't think so. Go back. So x minus 1500 over 225 equals 1.645.
Why minus 1500?
Should be x. It's a horribly written x.
Like I'm asking, like, why is it minus 1500?
Oh, why is it minus? Because we're basically going in reverse. Like on this is actually b. We had to standardize it, right, to get our z-score. But now we're going in reverse. We have this number. We have to back it out to get this number.
Is there, like, in the problem, what significant 1500? Like, what number? Is it the number of pairs or what?
1500 are mean.
Oh, okay.
So the mean hours, 225 is our standard deviation. Yeah. Now, how do I get rid of that 225 on the bottom? Multiply. I'm going to get x minus 1500 equals what? 370. 1.125 good. So add 1500 to both sides. X equals 1870.125. And this is going to be hours. Done. Questions on section 7.6? Okay, so dual credit, the 5.1 assignment that I gave y'all. Yes. That one kind of covers the first part of 7.6. I'm going to give y'all one tomorrow that'll be due Tuesday. That covers the second part of the problem solving part of 7.6.
Alright.
So, unfortunately for y'all, we're getting to a point where we're going to have homework almost every night, just like AP does. But the good news for y'all is y'all will get 2 days to do it. So, 2 days and 3 tries at that. So, that's just how the chapters fell. We're gonna all test Monday, and then the following week, we're going to all test that week as well. So we're gonna have 2 tests back to back where we're all testing. Okay. So let's look at 7.7. Now for dual credit, 7.7 is not even going to be tested at all. 4. Oh, go backwards. I'm going one way. I broke my board. What can I say? Okay, let's go back where we should be. There we go. So dual credit 7.7 isn't even something you need to know. AP 7.7 won't be on the Chapter 7 test, but it could be on the AP test. So we're going to look at how to assess normality if given some data. So some of the most frequently used statistical methods are only valid if our x's come from a population that's approximately normal. So what we're about to get into after we take our next test is only going to be valid if we assume normality. If we don't, I can't do it, sorry. So we need to look at a way to figure out, is our data normal? Can we do this? That's what we're going to do. So one way to do this is to look at a normal probability plot, which is a scatter plot of normal scores and their observed value ordered pairs. So their normal score is the x, the observed value is your y. We're going to do a scatter plot of these. So what should happen if our data set is normally distributed? Now, I realize this is what we're about to talk about, but anyone want to take an educated guess? What should our scatter plot look like if it's normally distributed?
Great.
Right. You actually nailed it. It should be a straight line, approximately. So, to set this up, let's divide. Let's say we're taking a sample where n equals 5. We want to divide the standard normal curve into 5 equal area regions. So what would each area be equal to if we're dividing it into 5 equal areas? 1/3. One fifth. That's what I'm going for. So each region has an area equal to 0.2. Why are these not the same width? I mean, they have the same area, but why aren't they the same width? That's right. That's right. So each region has 20%. They're not going to be the same width because the graph is taller in some parts than it is others. Even though it looks like there's more black right here than there is here. It's just because here we're spread out and we're tall, here we're short. So now we want to find the median of each area. So we'll take the first area, get the median. Second area, median. Third area, the median is 0. These are the median z-scores, is what these are. Fourth area, we're at 0.524. And then last area, we're at 1.28. Now, kind of following the width question, why are they not equal width? Why is the median not in the middle? Again, I mean, it looks like my median should be right here as far as the middle of each region. Why is it all the way over here? That's right. Perfect. So these are the normal scores that we would plot against our data. We wouldn't calculate these by hand, especially given each data point. We would use technology, whether it's calculators, statistical software. We would get help from technology to calculate these scores. If this showed up on an example or like a question, like you'll have on your homework AP, or like the example we're about to do, they'll say, here are the calculated z-scores. Here is the data. And sometimes they may ask you to draw the scatter plot. Other times they may say, here's the scatter plot. Is it normal? So in our n equals 5 example, this first median goes with the 10th percentile. 10th percentile. This one's our 30th percentile. 50th. 70th. And 90th percentile. Okay, so like I said earlier, we need to be able to assume normality to do a lot of our methods that we're about to learn. And so to do a scatter plot, we do the normal score on the x, observed value on the y. If we get a strong linear pattern, then we can say that it's probably going to be normal. It's plausible that we can assume normality if we get a strong linear pattern. Now, if they deviate from a straight line, that indicates there's some reason to assume that it's not normal. Maybe it's an outlier. Maybe it's not normal, period. It's not that it's an outlier, it's something else is going on with the data. It's skewed in one direction or the other. So curvature, like what you see in this one, where we start and then we follow a curve. That indicates skewness in the data. So that first graph on your notes, that says something is skewed. On the flip side, if we're pretty much in a straight line here, notice we're doing good, everything's staying along our line, and then boom, one pops up. The rest of the points aren't following a curve, they're following that line, except that one that's up in the air. That signifies an outlier. So now let's actually construct one of these plots and then use it to see if some data is normal. Okay. But since the values of the normal scores depend on the sample size n, the normal scores when n equals 10 are shown below. So they give us our normal scores. Notice they're in order from least to greatest. Then they also give us our data. Now, our data is not in a particular order right now, but we need to fix that. We need the data to also be least to greatest so we can make our pairs. What I'm going to do is I want us to order this data, and we'll just write next to the z-score which one goes with it. What's our smallest data value?
Yeah.
52.53. So that's going to go with our smallest z-score. So I'm going to cross it off because I've used it. Then we look for the next smallest. 52.66. I go with that z-score. I'm going to give y'all a second to go through and order them, pair them up, and then we'll talk about them. Okay, so which one of these again is our x? Is it the z-score or the observation?
Observation? Wait.
Z-score is on the x-axis. We want to draw a scatter plot where z-score is on our x-axis, the observation is on the y-axis. That's what we're going to do now in that next big blank on your notes. We're going to draw a scatter plot.
I'm putting it in for that blanket, is that okay, that's just at the table?
On the table you're putting in the blank?
Like those 4 numbers,
I mean, you can.
okay?
That's fine, but we also need to have room to draw the graph.
All the group. Okay. You're gonna do like a big graph?
It depends on how big your graph is. Like I drew mine big and it took up the whole space, but like I said, I drew it big.
Alright.
I'll give y'all a second to draw the graph and plot your points. That's what your scatter plot can look like. Something similar. It doesn't have to look exactly like that, but something similar. Okay, so if we look at our plot, we'll notice that our points should be approximately linear. Okay, where's my cursor? Let's see. They follow. I can't even draw a straight line. They follow pretty closely to a straight line. So it's plausible that the distribution of egg weight is approximately normal. Which that's the two blanks on the bottom of the page. Linear and plausible. If you're done with that, let's flip over to the next one. See, some still working, so I'll wait for y'all to finish drawing your graph. Okay. Now that we've actually drawn a graph and went through the process, like I said, usually we're not, if we were doing actual data analysis, we wouldn't sit here and draw the graph. We would use computer software to draw our normal probability plot for us, or a calculator. So that's what these next couple of examples essentially are doing. We have 10 in this first one, 10 randomly selected shut-ins that were each asked to list how many hours of television they watch per week. And they give us their results. We put them into Minitab, which is a statistical software, and Minitab gave them the following plot. So if we look at this plot, what can we tell from it based on what we've talked about so far? Is there anything you notice, anything you don't notice? What's happening on this normal probability plot? Is it normal? Is it not normal? Question. It's what? It's normal? Why do you say it's normal? It pretty much falls on a straight line, that's right. And notice that all the points fall nearly on a line, so it's reasonable to assume that the population of hours of TV watched by shut-ins is normally distributed. I'll go back. Okay, look at that next one. I know some are trying to finish up writing. If you're done writing, look at the next plot on your paper and see if you can determine any pattern about it.
So we're supposed to write something?
Well, if you wanna just make note of that plot,
How it's normal?
yeah.
Oh, okay. Gotcha. I missed something.
I mean, you don't have to, but it's up to you.
You know, I thought it was like something specific. I need to show. I mentioned, I redid the assignment, and it said I got a 96. But like, I re-entered it.
I had to change one this morning because I had it set to something called exam match. Let me recheck your grade after we finish and we'll see what happens.
Because it was the same number 5 that you were telling me about. And I can almost like, I can almost swear that I did it.
Yeah, I think I remember seeing this morning that it moved you to 100 when I made a change. What it was, not that it really matters, but when I put in those answers, I wanted to do what's called pattern match. And the notation for that, y'all have to don't write this down, I'm just explaining something. So the notation to tell the computer that you put in an 88. So I wanted to do pattern match, meaning you can put in 88 or 88.0 and it takes it. So I had to put these parentheses with this question mark, which tells the computer that part's optional.
I got you.
Well, I didn't change this to pattern match. I left it as exact match until this morning. It was saying you didn't put in these parentheses with the question mark, it counted it wrong.
Right.
So when I changed it, it recalculated the grades. So, yeah. But I checked that, I'm like, based on what we talked about, you should have 100, didn't you? I don't know what happened.
Yeah, so I thought I just entered something wrong again.
No,
Thank you.
you're welcome. Okay, next one. So a sample of times of 15 telephone solicitation calls was obtained and is given below. Minitab obtained the normal probability plot on the next slide. So here's our plot that Minitab gave us. What do we notice? Yeah, there's some kind of skew going on here. I mean, we could almost make a logistic curve with our graph here. Something's going on. So can we assume normality on this one? No, you can't.
That's not a straight line.
Yeah, no, that's not a straight line.
I got a 90.
So specifically, the pattern has a distinct nonlinear appearance. It is not reasonable to assume that the distribution of lengths of calls is normally distributed. You can almost assuredly say it is not normal. There's something going on. So what we're going to have to do here, well, we're not going to have to do it, we're going to talk about it, but we're going to have to find a way to transform this data to be able to interpret it. We can't interpret it like it is, we've got to transform it into something that we can interpret. That's what we're about to talk about next, on the next slide. y'all excited for the first home game?
This, we're working on it.
Working on it.
Yeah, I think we'll be good. But we just,
What happened last week?
uh,
Or is that something y'all are trying to forget at this point?
we're just trying to figure out what's going on with us.
Yeah.
I mean, we're fine. We're missing a lot of people. I'm not gonna use that as an excuse, but,
Yeah.
yeah. 'Cause last week we were out, we had our starting center was gone. And, our starting center was gone, our running back was gone, our receiver was gone. All three of them guys were out. So it was, we were planning on method, but we should have won. You know? We just were playing this,
Yeah.
I'm sorry, I thought you had Alabama in this corner for a second.
Won't see me wearing one of those.
That's why I was confused. I thought I saw the A. They switched over.
Funny you say that. Someone this morning that doesn't have me, but their friend does, came in and they're like, based on what you're wearing and what you have on your wall and everything, I would say you like A&M. Maybe. Only had 2 degrees from there. I don't know if I can say I like them or not. Okay, last part. Last like 5 minutes, basically. Okay, so we want to transform the data. We've got to achieve normality to be able to analyze it. So how can we do that? Well, when the data is not normal, it's common to use a transformation. And so when we show positive skewness, which means a long upper tail, remember, usually a logarithmic transformation is applied. Meaning we take every observation and take the logarithm of it. You can also do the square root, cube root, and other transformations to the data to determine which transformation best normalizes the data. And when you're using statistical software, I mean, yes, there's methods to try to say, oh, I think this one's the best. But honestly, even when I was analyzing data in college, I would just start with the logarithmic, see if it works. If it doesn't, okay, let's try square root. Let's try cube root. Let's try exponential. Something's got to work. I just kept trying to find one until it finally looked normal, and we're like, okay, this is how I transformed it. Let's look at an example. So the data comes from table 7.4 in your book about plasma and urinary AGT levels. I have no clue what AGT stands for, but we'll go with it anyways. Only AGT I know of, I know it's not talking about. So when I hear AGT, I think of the show America's Got Talent.
I'm not sure.
A histogram of the urinary AGT levels is strongly positively skewed. Notice it's got our distinctive positive skew shape. Comes up and then boom. Oh, not like that, but you get me out there.
You're right.
It's skewed right. That's right. So now, if we take the logarithm of all of our values, watch what happens to the graph. Boom. Which one looks more normal? The logarithm. So a logarithmic transformation is applied to the data, and now it looks a little bit more symmetrical. That's it. Chapter 7 is complete.
Ready for it?
I don't know, maybe you want to study, maybe you want to homework.
So I have a question. Is that gonna be just like, last time, where it's like 10 vocab words, 10 points, and then 9 points?